Okay, for a continued discussion about ways we calculate and determine the numbers of moles and grams of one reactant needed to react with a given number of moles and grams of another reactant, we call this stoichiometry. Or we can do this for reactants and products, either one, that result from a particular reaction. So some people will view stoichiometry as an epic battle, and we'll have to decide who wins, the student or the stoichiometry. Well, let's hope we can make the best of this and get there successfully. Well, stoichiometry requires a bunch of proportions that we need to pay attention to. The relative proportions in which elements form compounds or in which the substances react gives us stoichiometry. And in order to do that, we need to understand that it's always related to the moles. It's always based on a mole per mole, which is equivalent or similar to talking about molecules reacting. Moles are just multiples of molecules. And so we always have to come back to the mole ratio between the things in a reaction. So if you have A and B combining to make C and D, the number of grams of A can be related to its number of moles using a molar mass. And those are not hard to do. Remember, the units are going to be grams per mole. And then once you have that, you can determine the mole ratio between the two reactants, A and B, using coefficients from the balanced equation. So you always have to have the balanced equation before any of this makes any sense. Once you've determined the number of moles of B, you can determine the number of grams it requires using its molar mass. Again, the same idea, grams per mole. And as long as you set these things up carefully, write them out so that the units are shown, there are much better chances of success. All right, let's try some. All right, an aqueous solution of sodium hypochlorite, aka bleach, is prepared by reacting sodium hydroxide with chlorine gas according to the reaction that's shown here. And what we have to determine in this particular question is how many grams of sodium hydroxide are needed to react with some amount of chlorine. So what we're looking for is, given a certain amount of chlorine, that would be our substance A from the previous slide, how much sodium hydroxide is going to be required to go with it. So we're going to think in terms of A and B from the previous example and use molar mass, a mole ratio, and another molar mass to determine the number of grams of sodium hydroxide required. Another way of looking at that is using a chart that's shown in your textbook. For any balanced equation, you're going to be going from grams of A to moles of A to moles of B and grams of B. And sometimes they're going to be intermediate portions of this, but we're going to give you the full method here. So how many grams are there needed? So to get from grams of sodium hydroxide, so if you have 25 grams of chlorine, we need to be able to get to moles of chlorine. And so in order to do that, we will use a molar mass and the molar mass of chlorine to give us the moles of chlorine in the reaction. We will also need to have, so that would be the molar mass right here. We will also need the coefficients from the balanced equation. That gives us what we call a mole ratio. And then we will also need to determine, once we have the moles of sodium hydroxide, we'll end up with moles of sodium hydroxide after a certain step. We'll look at that more carefully. And then we will again use a molar mass to get the grams of sodium hydroxide. So let me write the other one in between. Between having the moles of chlorine, from the moles of chlorine, you can get, using the mole ratio, using a mole ratio, you will get the moles of sodium hydroxide that would correspond. Okay, so we're going to use a mole ratio here and 2 molar masses to get to the destination in this question. All right. So let's follow the steps. Starting with your 25 grams of chlorine, we're going to need to determine its number of moles. So the number of moles is determined using its molar mass. And for chlorine, 1 mole of chlorine should be, think about it, look at your periodic table, twice chlorine's atomic mass of 35.45 should give you 70.9 grams of chlorine. And then from that, we're going to be able to use a mole ratio. with the moles from the balanced equation, we have 2 moles of sodium hydroxide that are going to react with 1 mole of chlorine. In other words, there's nothing here, so we interpret that to be a 1. And notice as we go, when this is set up correctly, the moles of chlorine canceled, the grams of chlorine canceled. The answer we want is not moles of sodium hydroxide, so we don't stop here. We'll keep on going, and again, the next step is after the mole ratio is to use another molar mass. This was a molar mass, and now we'll use a second molar mass. The molar mass of sodium hydroxide, think about it. If you look it up, sodium is approximately 23, oxygen is 16, hydrogen is 1. It comes out pretty close to right on 40. And that's 40 grams for 1 mole of sodium hydroxide. Again, having set this up correctly, you should notice that the moles of sodium hydroxide are canceling out, and what you wanted, namely grams of sodium hydroxide, should be the remaining value. And put it all in a calculator, and you have a number. No one's going to do this in their head. That's how we do these things. OK, let's do another reaction that we might find interesting. And we'll see if we can make sense of the stoichiometry. If lithium gas is going to react with water to produce hydrogen, lithium metal is going to react with water to produce hydrogen gas, how much hydrogen gas would you get if you have 100 grams of lithium? Well, let's think about that. What do we have to do? First, we're going to have to write the balanced reaction and realize that the other product is lithium hydroxide. Sorry for sneaking ahead on you there. And so what will we do? So lithium reacts with water. And so lithium and water is going to make hydrogen gas. And lithium was a solid. Nice to pay attention to these phases. They'll be more important to us as in various places, but it's a good habit to think about them now. And then we'll make lithium hydroxide is the other product. This turns out to be what we describe as aqueous because it's dissolved in water. And in order to get this balanced, I just put the numbers in for you. The 2 goes in front of lithium hydroxide. Oops, didn't need that extra part. And a 2 in front of the lithium in the front. Now we have a balanced equation. Given that balanced equation, we can begin to make the calculation. So begin with what you're given, namely the 100 grams of lithium, 100 grams of lithium. And we always have to start with a molar mass. In this case, it's simply an atomic mass because it's not a compound, it's just the element. So 1 mole of lithium corresponds to 6.941. Take all the sig figs you're given because it's usually smart. This question should be interpreted to have a decimal after the 100, or we'll have few sig figs in the result. And having done this much with the grams and moles of lithium should allow us to cancel out grams of lithium. But the moles of lithium is not the answer we want. We want to know how much hydrogen gas, in other words, in mass for hydrogen gas. So keep going. So now we need to relate the moles of lithium to the moles of hydrogen produced in the reaction. And now we go to the balanced equation. The numbers we need are going to be right here, the coefficients. So if you see 2 in front of lithium, that belongs in this lower portion of this mole ratio. Remember, this is called a mole ratio. Apologies for the extra line here. I'll try to make that a little bit cleaner. And so the number on top is the coefficient in front of hydrogen in the balanced equation, which if you don't see anything means you put in a 1. And so at this step, the moles of lithium have canceled out, and we haven't got to the correct answer yet because we still want to know the amount of hydrogen. So we have to determine how many grams that will be. So the first step we used was a molar mass. The last step is also a molar mass. And in this case, how many grams there are per mole of hydrogen. And if you don't think too hard, the molar mass of hydrogen, H2, remember it's diatomic, is 2.016 grams of hydrogen. Check your periodic table to remind yourself that it's 1.0079, and we'll call it close enough to 2.016. That's enough sig figs for this exercise. And at this step, the moles of hydrogen are now going to cancel. And then the rest of this becomes a math exercise. And if you put your calculator together, put your calculator to work, give yourself a chance and try it. Pause the recording to do so if you wish. My number that I came up with is 14.5 grams of hydrogen. If this is taken to be a 3 sig fig value, then we should report 3 sig figs in an answer. So this is a stoichiometric calculation with the same usual steps. One step is the molar mass, the second step is the mole ratio, and the third step is the second mole ratio, or molar mass. Okay, let's do another example with stoichiometry. This one's a little bit different. See if you find it interesting or helpful to you. We're going to look at an interesting reaction in potassium chlorate that generates oxygen gas when it's heated. And whenever you do these kinds of reactions, you're always going to have to write the balanced equation for the process. So it's potassium chlorate. Remember your names of ionic compounds. Chlorate is ClO3 single minus anion with potassium. And it's going to generate oxygen. The other product turns out to be potassium chloride. And if you look at this reaction, we're going to have to balance it first. So what's missing? Well, we've got funny things going on with oxygen because you've got 3 on the left and 2 on the right. So here's a case where you're typically going to add coefficients to both sides to make them come out even. That gives you 6 oxygens on each side. But now we've changed the number of potassiums in chlorine. And in order to make it come out even, putting a 2 in front of potassium chloride should work out. OK, now, what are we going to do? If you have a given amount of potassium chlorate heated up, we want to find out how much oxygen is going to be produced. So let's set this up and see what kind of steps we'll have to take. So this would be like substance A in our scheme, and the oxygen will be the destination, the one we're trying to find in our stoichiometry problem. Start with what you're given. Give yourself lots of room when you write these out. The steps require some space. If you're going to be careful about it, you need to write all the pieces in to get it right. Otherwise, we overlook things without noticing. So you have to look up the molar mass and determine the molar mass of potassium chlorate. And I've done it for you. So it's 122.45 grams. Turns out to be 1 mole of potassium chlorate. Put that down here, too. That makes sense. Potassium chlorate grams per 1 mole of potassium chlorate. And the reassurance to know that you're on the right track is to show you that the potassium chlorate grams should be canceling out. OK, so that was our molar mass for the first step of the stoichiometric calculation. Now, this next step, we're working our way towards oxygen. How much mass of oxygen, in other words, grams. In order to do that, if we're going to have to get rid of moles of potassium chlorate. So put moles of potassium chlorate on the bottom here. And we're relating this to the moles of oxygen. We always have to go back to the balanced equation here for this sort of thing. And so what are we putting in for values? Well, we're putting in what we see for coefficients. So 2 moles of potassium chloride reacts with 3 moles of oxygen. Having done that, the moles of potassium chlorate, oh, I said the wrong one. Potassium chloride is also 2. Potassium chlorate will cancel out. And now if we stopped here, we'd have moles of oxygen, but we don't want that. We want something more. And so from here, we're going to continue with the calculation to, let's see if I can make that disappear. There we go. Then we're going to calculate the mass of oxygen from that number of moles. So what we need is a molar mass, again, molar mass, and I forgot to write this in. This is a mole ratio. Step 2 is a mole ratio. Step 1 is a molar mass. And then step 3 is the second mole ratio. Sorry, molar mass. I keep saying the wrong mole thing. Sorry about that, folks. And so what we're looking for now is something that will cancel out the moles of oxygen relating to its grams. So 32 grams. Remember, it's diatomic oxygen again. And so diatomic things are always got to be calculated accordingly. And that should do it. That will give us grams of oxygen as a result. If you put that together, take a pause in the recording right here, and use your calculator carefully, you should come up with an answer that would be grams of oxygen. And mine, when I did it, I came out to 80.4 grams. Given a 3 sig fig answer, or value to begin with, a 3 sig fig answer here is appropriate. I've used plenty of sig figs on that molar mass. The other molar mass for oxygen, I could have put in more, but it really is 32.00 anyway, so I wasn't reducing the number of sig figs in having done that. Another way of looking at stoichiometry problems is described by some people is thinking about this in a macroscopic versus microscopic level. So the macroscopic world, we're talking about masses. Macroscopic world of the grams of reagents in the process. And on the microscopic level, it's where the actual atoms and molecules are reacting. And so we have to use a combination of things that relate to the macroscopic, namely the molar mass, because that gives us grams per mole. And things that relate on the microscopic level is the mole ratio, because it's looking at how the actual atoms and molecules come together in a balanced equation. Don't forget, you always have to have the balanced equation for that to make sense. All right, that's just a different way of representing this grams of A to grams of B series of steps, same kinds of steps, but it's kind of an interesting way to think about it, to realize that we're looking at the macroscopic and the microscopic, and we go from the macroscopic to the microscopic and back to the macroscopic to be able to measure things in grams. Okay, I hope you find these examples helpful. Let me know if you have questions. Good luck on your homework, and see you in class.